Okay, 6th graders, here is your second flipped lesson. This is for Thursday night, August the 9th, and tonight we're going to be talking about rational and irrational numbers. And this gets a little tricky, but every number fits into one of these two categories. A rational number, the first definition is any number that can be written in fractional form. So if a number can be written as a fraction, then it has to be rational. And some examples are 1/3, 2/10, which we know that can be simplified, but for the sake of just talking about it, it is a rational number, and -5/8. So don't let this negative symbol fool you. We do have negative fractions, and negative fractions can be rational numbers. Now the technical definition, when we have two numbers and that are represented by variables A and B. A and B are both integers, and integers, and we're going to talk about the definition of that in just a second, and B does not equal 0. So B cannot be a 0, and that is a generic definition for rational numbers. Now to back up a little bit, integers. Integers are whole numbers, positive or negative. So when you come into class tomorrow, and if you will notice up above me, there is a number line, positive all the way to positive infinity, and it goes all the way to negative infinity as well. And you can see this better when you get into class tomorrow. I'm sure you've probably seen it already. But whole numbers, positive and negative, are integers. Alright, slide this over for just a second. Rational numbers can also be decimals, but only if they are repeating or terminating. We talked about this on Wednesday. We know that a repeating decimal has a pattern. A terminating decimal, it ends, it terminates, it stops. So some examples of repeating decimals would be 3,333 ten-thousandths, but as you can see, this line indicates that the number goes on forever. It is repeating, it is predictable, it has a pattern that I can tell. A terminating decimal would be 8 and 125 thousandths. So that would be an example of a repeating or a terminating decimal. These are both rational numbers. This one's rational because I can see where it's going to go forever, and this one is rational because it stops. Irrational numbers. Now you'll see that they're written in red, the definition. It's not that they're negative, or it's a negative word, it's just a different type of number. Irrational numbers are decimals that do not repeat or terminate. And the best example that I can give you is pi. We talked about pi in class. This is the symbol. This is the Greek spelling. 3 and it goes on forever, and these dots indicate that it goes on forever. But what you'll notice is that there is no discernible pattern. And we talked about mathematicians that spend their lives calculating the next digit of pi, and someone else brought up in class that there are supercomputers that run constantly, and they've calculated pi up to so many digits, and I don't know what they've got up to now, but they have contests for this as well. But this is definitely an irrational number. Some other examples of rational numbers are square roots of numbers. Basically, if it doesn't repeat and it doesn't end, it's an irrational number. Now, I've got a couple practice problems for you to do tonight. Again, they're practice. You can try them if you want. I would encourage you to try them. And you just have to tell me if it's an irrational or a rational number. Irrational or rational. The first one is 3/4. The second one is the square root of 2. And yes, you can look at your calculator for this one if you want to figure out your scientific calculator. 3, 5 and 3,636 ten-thousandths. And notice the line here. And then the last one, I'm not even going to say the decimal. You can see that it is 3.14159265. So try these out, see how you do. Good luck, and we'll go over this tomorrow, which will be Friday, August the 10th.